Hey everyone, welcome to Neural Notes, show where AI comes alive. Smash that subscribe button and ride the innovation wave.
All right, let's jump right in. You know those problems that seem totally impossible at first glance, but then the solution is so simple, so elegant, it's just beautiful? Well, that's exactly what we're tackling today. We're talking about the one idea that basically makes all of calculus work. So here's the big puzzle. Picture a curve, like a roller coaster track. Finding the average slope between 2 points, easy. We've been doing that for years. But what about the exact steepness right at one single instantaneous point? How in the world do you measure that? You see, our trusty old slope formula, rise over run, it's great, but it has one requirement. You need two different points. You connect them, and that line is called a secant line. Simple enough. So the logical thing to do would be, well, if we want the slope at one point, let's just take our 2 points and slide them closer and closer and closer until they're sitting right on top of each other. Makes sense, right?
Well, here's where we hit a massive brick wall. The moment those 2 points become 1, look what happens to our formula. The rise on top becomes 0. Okay, no big deal. But the run on the bottom also becomes 0. And boom, we're left with this. 0 divided by 0. I mean, that's the ultimate no-no in math, right? It's undefined. It's like our standard math rulebook just caught on fire. We tried to divide by 0, and the whole system just crashed. This is where the sheer genius of calculus comes into play. It flips the question on its head. It says, okay, what if we don't actually land on the point? What if we just sneak up on it? What if we get so incredibly, ridiculously, infinitely close that we're basically there without ever actually arriving? And that incredible idea has a name: the limit. A limit isn't about where the function is at a point. No, it's all about where the function is headed. What value is it getting closer and closer to as you approach that point? So, to really see this in action, check out this graph. It's a perfectly normal line, except for one tiny little detail. See that? There's a hole in it, right at x equals -1. So let me ask you a trick question. What's the actual value of the function right at x equals -1? The answer? There isn't one. It's undefined. There's literally a gap in the graph. The function just doesn't exist at that one specific point. But now, let's ask the calculus question. Forget about what's at -1 for a second. If you walk along the line from the left and you walk along the line from the right, what y value does it feel like you're about to step on? You're headed straight for 2.5 from both directions. And that is the entire idea. We say the limit of the function as x approaches -1 is 2.5, even though the function never actually gets there. It's about the journey, not the destination. Now, this idea of checking from both sides is absolutely crucial. It's not just a nice thought, it's the rule. To be sure about a limit, you have to look at the approach from the left and the approach from the right. And we have special names for these. When you come from numbers that are smaller, that's the left-hand limit, and we use a little minus sign to show it. When you come from numbers that are bigger, that's the right-hand limit, and we use a plus sign. So this brings us to what I like to call the golden rule of limits. It's actually super simple. For a regular overall limit to exist, the journey from the left and the journey from the right, they have to lead to the exact same destination. That's it. If they don't agree, the limit doesn't exist. All right, theory time is over. Let's put this new superpower to the test. We're going to look at a trickier graph now, what's called a piecewise function, where the rules kind of change midway. This will really show us what's what. Okay, let's focus on what's happening around x equals 2. First things first, let's just look at the journey from the left side. As we get closer and closer to 2 from below, where is the graph headed? If you follow that path, it takes you right to a y value of 3. So we say the left-hand limit is 3. Got it? Good. Now hit the reset button. We're still going towards x equals 2, but this time we're coming in from the right, from all the numbers bigger than 2. What path are we on now? Totally different story, right? From this side, the function is heading straight for a y value of 1. So our right-hand limit is 1. So now it's time for the final verdict. We apply our golden rule. The left side says we're going to 3, the right side says we're going to 1. Since 3 does not equal 1, the two sides don't agree, and that means the overall limit as x approaches 2 does not exist. We just write D and E. Okay, this last part is so important because it really separates the limit
from the actual value. Let's look at what's happening at x equals 4. The path, the approach from both sides is clearly heading toward that hole at y equals 2, right? So the limit is 2. But look at that solid dot way up there. The actual value of the function at 4 is 4. This shows you perfectly that the approach and the actual destination can be two completely different things. So, let's boil this all down to the 3 big ideas you need to remember. 1. A limit is all about the approach, not where you actually land. 2. Because of that, a limit can exist even if there's a hole in the graph. And 3. The golden rule. For an overall limit to exist, the left and right sides have to agree. You see, this whole idea of the limit, it's the secret key that unlocks everything in calculus. It lets us solve that slope at a single point problem and a million other things by giving us a safe way to deal with infinity. So I'll leave you with this thought. Now that we have this key, what other impossible doors are we finally ready to unlock?